In 1982, computers were excellent at calculating numbers, but they were effectively blind to geometry. If you wanted to draw a shape, you were constrained entirely by rigid grids of pixels. To put that shape on paper, you used a dot matrix printer. The computer had to send exact X and Y coordinates to the machine, instructing it precisely where to strike an ink ribbon to leave a mark. This reliance on fixed grids created a severe scaling problem known as aliasing. Enlarging a small circle did not add more detail, it simply magnified the jagged staircase edges of the original pixel grid. Engineers called this device dependency. Because every printer model had a different grid resolution and its own mechanical language, a developer had to write custom software for every single printer on the market. Because of this physical bottleneck, digital graphic design was practically impossible. Personal computers were largely restricted to processing basic text. At the time, two researchers named John Warnock and Chuck Geschke were working on this exact problem inside Xerox PARC. Xerox dominated the professional printing market. Their business relied on selling massive, dedicated mechanical typesetting machines that cost upwards of $150,000 each. Warnock and Geschke had actually developed a software solution called Interpress to fix the scaling problem, but Xerox management rejected it. Releasing software that allowed cheap computers to print complex graphics threatened their highly lucrative hardware monopoly. Realizing their research would never see the light of day, Warnock and Geschke left Xerox in 1982 to found their own company, Adobe Systems. By refusing to adapt, Xerox inadvertently created its own greatest competitor. Warnock and Geschke were now free to bypass physical typesetting machines entirely, representing visual data through geometric logic instead of physical hardware. To break away from the physical grid, Adobe engineered a shift from raster graphics, which send thousands of discrete dot coordinates, to vector graphics, which send a geometric equation. The foundation is the Bézier curve. It requires only 4 coordinates: start, end, and 2 invisible control points. These feed into this exact mathematical formula, calculated in real time. Manipulating the control points recalculates the equation instantly, bending the curve continuously without fracturing into pixels. By utilizing mathematical equations instead of rigid grids, Adobe guaranteed that a shape could possess infinite resolution. The smoothness of a curve is limited only by the math itself. Adobe packaged this mathematical framework into something called PostScript. Rather than a static image file format, PostScript operates as a Turing-Complete programming language, fully capable of logic, loops, and calculation. When a computer uses PostScript, it does not send a pre-rendered image to the printer. It simply sends the mathematical instructions for how to draw the image. The receiving printer uses its local processor to read the code and draw the highest quality grid its hardware can manage. A cheap printer maps the math to a 300 dot per inch grid, while a professional printer maps the exact same code to a 2400 dot per inch grid. This severed the link between the computer and the printer. The computer no longer needed to know the physical constraints of the output device, rendering the hardware brand completely irrelevant. There was, however, a severe compute tax to this solution. Calculating advanced geometry on the fly required immense processing power that most personal computers in the 1980s did not possess. Steve Jobs recognized the potential of this mathematical approach. In 1985, Apple partnered with Adobe to build a piece of hardware that could handle the computational load, the Apple LaserWriter. To make PostScript work, the LaserWriter required more RAM and a significantly faster processor than the Macintosh computer it was plugged into. Inside the printer chassis was a Motorola 68000 processor, the exact same high-performance silicon die used in early desktop workstations. The LaserWriter functioned as a dedicated graphics supercomputer, tasked entirely with translating mathematical equations into light and ink. This combination transformed the economics of printing. Within a few years, the cost of professional-grade layout fell from 6 figures to the price of a desktop peripheral, shifting control from industrial shops to individual creators. A few years later, Warnock initiated Project Camelot, an effort to evolve the PostScript language into a universal consumer-facing tool. We know it today as the Portable Document Format, or PDF. The PDF utilizes the exact same device-independent logic to guarantee that a digital layout looks mathematically identical on any screen, anywhere in the world, regardless of the operating system. This mathematical foundation became the industry's universal language. Because professional printers and high-resolution displays required PostScript or PDF to function, any design software, from Photoshop to Illustrator, had to be built around Adobe's core engine to remain compatible. Adobe's market position wasn't built on a better user interface. It was built on a mathematical translation layer that every professional in the world was forced to adopt. By solving the foundational geometry of digital rendering, they permanently encoded visual information into pure, scalable math.